All right, 9 o'clock. The people online, if you can hear me, please say something.
Good morning, Professor.
All right, great. Thank you. Okay, so we are finally back on campus. It's been a long break since what? Late September, I guess it was. Yeah, all of October online. Anyways, today we are continuing with sequences and series. We'll do a little bit of review of the summation notation idea. Sorry, no, today's the first day, we'll see that. So we'll review arithmetic sequences and series. We have a formula for the general term of a sequence, of that kind of sequence, and we also have a formula for partial sum. So we'll review those and then talk about a slightly different way of writing the sequences, which you've probably seen before, and then look at the same sorts of things with geometric sequences. So a different kind of special type, general term formula, partial sum formula, and infinite sum formula. And if things go well, we should have just a moment to preview some ideas that we'll be needing to talk about interest in our next class, which is our main application of this. So last time, just vocabulary we're talking about, we have a sequence, which is just some kind of list with a pattern or rule. For the things in the sequence in the list, we call them terms and represent them like this is an for any general term. A series is a similar thing. Sequence A1, comma, A2, comma, A3, comma, dot, dot, dot. Series is just adding them together. So A1 plus A2 plus A3, etc. All right, partial sum, and this is just the sum of the first n terms. N is just whatever number you want. The beginning of that sequence to whatever n you have chosen. All right, we did not see partial sum for arithmetic sequences because we don't really need it. If you're just adding up a bunch of numbers to infinity, the result will just be positive or negative infinity. But it turns out our answer for that is a little more interesting with the geometric sequences. Okay, first thing, summation notation. It's just a way of writing sums of numbers. So writing a series. If you haven't seen this before, the thing, sorry, let me one quick step back. This thing here is the capital Greek letter sigma, and sum starts with S, and it might not look it, but this is where the English S character comes from, Roman alphabet S character. So S and S, so someone thought this made sense and seemed connected. So this thing just means add up all of the items that we will have. So the actual items. The thing in front is the general term of the series. So that's the actual thing that was defining what we'll have in the series. The number on the bottom is our index. This is telling us how many there will be. So let's start when I is equal to 1. We have I here, and go until I is whatever number is on the top, n, and then stop at that point. So it's telling us how many we'll have. And again, the big sigma E looking thing here just means once you've made all of those things, add them all together. So it's a series. Some examples here. Right, this is just the actual, like what this means, just written out in words. if we were to read this out loud, it would be the sum of AI from I equals 1 to n. Which is kind of formal, kind of English way of reading that. Some examples of this. So in a more general sense, it's like this here. So AI could be anything, just, I don't know, 2 times that or that squared or whatever. But okay, so figure out the first one, figure out the second one, and the third one, and the fourth one, etc., until n, whatever n we've chosen, and then stop, and then we add them together. So that's just kind of expanded on what this represents. Very practical, just very simple version of this would be what we have in the bottom right here. So our general term is just I, not even multiplied or added with anything, just that. And we can start, usually we'll start at 1, but we can start anywhere. So start when I is equal to 4 and calculate the front term. Well, if it's not being multiplied or added to anything, it's just 4. And then we take our index, increase it by 1. So it's 5. And then, right, so 5. And then we increase it again, we get to 6. We notice that here when I is equal to 6, that's the number on top. So we stop there. So not too complex, but it's a nice, just sort of compact way of writing maybe a very large sum of a whole bunch of terms being added together. We can represent a complex idea with just one little small thing like this. So efficiency. All right, let's try this out. We'll also use this to review the formulas that we talked about in our previous class. So let's find the sum of the first 7 terms of this thing. We'll get our number. And then after that, we'll try to rewrite the series here using that summation notation. So try this first. And tell me what you get. All right, do we have an answer? 168. Okay, so we are saying that sum of the first 7 terms, S7 will be equal to 168. All right, let's check this. So what's the formula? What is our general formula for the sum, partial sum for an arithmetic series? N over 2. A1 plus an. Okay, so here we'll need n, which we have. We don't have a1 or a7 here, but we can figure those out pretty quickly. So S7 then is 7 over 2. A1, like we have our general term here, it's very quick to figure out what those are. So 6 times 1 for that, so just 6. And on the other side, 42, 6 times 7. All right, so 7 over 2 times 48. And I would simplify this as 7 times 24 And then, okay, it's going to be 168. All right. Let's just see if we remember our formula, our general formula for, or formula for the general term of a arithmetic sequence. Okay, one. Okay, like we can put the d or the n-1 first or second, doesn't matter, but those two parts. All right, so we figured this out. Let's see if we can rewrite this in our summation notation using this kind of representation. So we need the big E thing. And what is our starting index here? 1. So it will almost always be 1, especially for these kinds of sequences. It doesn't need to be, but almost every example we have will be starting at 1. How far will it go? 7. So 1 on the bottom, 7 on the top. What's the actual general term here? Okay, so when we write them like this with this general term, n is the number that's sort of changing and slowly going up. But when we write them like this, n is just the final number. The thing that's changing is I. Okay, so this is just kind of a general term, but what is the term? What is AI? How do we calculate that? So I should be in there somewhere. 6i. 6i. Okay, so let's check that. Here, if we have this general term, we saw that the first term is 6. What's the second term of this? 12, second term. And then, okay, we're adding 6 each time, so 18. Okay, so we get the pattern. So let's look at our summation notation, see if we get the same thing. All right, so our A1 would be equal to when I is equal to 1. So 6 times 1. Okay, so 6. What would the second term of this thing be? Okay, also 12, because I would go up to 2. 6 times 2 is 12. And then we can probably recognize the pattern. 15. So it's the same thing. This general term, the summation notation gives us the same result. So we've done it right. We've figured out the correct way to write this. So it's always easy to check your work by just actually making a few of the terms, making sure you have the same thing on both. All right, another example. You can try this one too. So sum of the first 4 terms. I know it's not very many here. And then trying to rewrite in summation notation. .28. Okay. S. S4 equals. Okay, well, I'll give people another few moments to work. If you've gotten this part, also try to do this, rewrite in summation notation. All right, let's try here. So our let's try our other formula for a partial sum. Right here. What's the other version of this formula? Partial sum n over 2, and the part inside the brackets is a little different. We take the other formula and our an term and just expand that to a1. So we had one a1, but then if we expand the an term, then we get one more a1, and then the rest is the same there. Okay, so if we're going to use this formula, then we need a few different parts. So we need our n, which is 4. We need our a1, which we don't have, but what is the first term? 1. So 4 times 1 minus 3, 1. We need d as well. What should our d value be here? Okay, so the actual number, 4. We could figure this out by finding maybe 2 or 3 of the terms and just looking at the difference. But once we have a deeper understanding, we can see this is just kind of always going to be there on the end. The difference is going to come in from whatever's being multiplied by that index value, multiplied by n or multiplied by I. So our d is going to be 4. All right, so we have all the parts for the formula. S7 then is equal to, sorry, 7 was the last one. That's 4 over 2, 2 times a1, which we said is 1, plus 4 minus 1, 3 times 4. Okay. 2 times 2 plus 12. 2 times 14, so 28. So I know we're doing these with really simple things and just only 4 terms. Rather than use the formula, it'd probably be easier to just manually write out the terms and add them up. It'd be really quick, but we're just practicing using these formulas. We don't always deal with really small situations like this. Summation notation, if we rewrite here, so write our better, nice big sigma here. What's our index on the bottom? All right, so let's start I equals 1. And on the top, 4. All right, the general term? Okay, 4 I minus 3. Most of the time, it's just going to look the same as whatever your general term thing is. There are other special cases and other stuff we can do with the summation notation, but for arithmetic sequences, usually pretty similar. Just quick notes here. When you look at the index variable that's used here, it's usually I or maybe J or K. You know, it could be anything, but these particular ones are often used here, so it's good to just be familiar with the common variables that are used and see it all kinds of textbooks. All right, let's move on. So let's switch this to the other side where we'll have a summation notation thing like this and try to write it out. What does this actually represent? So expand and then actually add them together. $30. Just a few more seconds. Okay. What is the first term of this going to be? 2. So here we have a j index. So we start when it's 1, put that here, 2 times 1, okay, 2. Next term, 4, okay, so this is 2, 2 times 2, 4. You can probably see what's going to happen here. This is 3, that's 6. And then 4. How far do we go? 10, because that's when our index hits 5, and it says that's when we stop. All right, that's pretty easy to add up. 30. Okay, so that's all we have to do. And one more of these, a little more complicated. This one, probably not convenient to write them all out. So trying to look at this, figure out what the parts are, and use one of our formulas to get the answer. Okay. Okay, let's try this out. So all the parts that we'll need here, we have our partial sum formula. So S25. We are going to need n. We have our n value. Let's move this over. So n is equal to 25. What else are we going to need for this formula? Okay, so we could use, what's the first thing that we'll definitely need? All right, so our first term, what is our first term? 11, so just 1 here, 4 times 1 plus 7, 11. And then we have our 2 versions of the formula. We could figure out the 25th term, or we could figure out our d value. We can see what the d value is here. 4. Okay. So seems like we can just use that directly. So 2 times our a1, which is 11, plus our n minus 1, 25 minus 1, 24 times 4. And we just evaluate that. So 25 over 2, 22 plus 24 times 4, 96. 25 over 2. All right, and our number in here, 18. So just trying to simplify. Lots of ways we could do this. I would just take out the factor of 2 here. by 59 here, okay? And if we could do this with long multiplication, yeah, so this is the 1,475. If I were doing this in my head, I would just think of this as 25 times 60 minus 25 times multiplied by 1. Because 59, that's 60 minus 1. So, okay, so here's the 1,500, and then just the minus 1 here, 1,475. These kinds of mistakes with the formulas for getting the minus 1 is really common, especially when we get to the geometric ones, and then we see that some kind of don't have that. So which formulas have the minus 1, which one don't? The thing you have to be careful about when trying to remember. Okay, so good review of these formulas and also how to work with this summation notation here. Let's go on to the next part, which is geometric sequences. For the previous ones, all the arithmetic sequences, they were built on addition. We had that D value, common difference. We just added that each time. Geometric sequences, we have almost the same thing, except we have R, which is a common ratio. So we multiply by the same thing each time. The rest of this is the same, kind of very similar concepts. The R value needs to be the exact same thing each time. Otherwise, or if it's not, then it is not this special type of sequence, which again, we see very often in lots of practical applications, lots of useful formulas that we can know for this, so useful to identify. So just like we had with our D value, R is going to be equal to A2 over A1. That will give us R, and that's of course equal to A3 over A2, A4 over A3, etc. So if we divide the two of any two sequential terms, we'll get back to our R value. All right, so let's look at a few here. So we can look at each of these and try to figure out if these are geometric or not. All right, first one. So is it geometric? So we should be looking at what we are multiplying by. So going from 4 to 8, what do we multiply by? 2. And 8 to 16, also by 2. And look at, okay, are the rest of them 2? Yes, yes, yes. Okay, so yes, geometric, common ratio between all of them. Next one, -2 to 6. Okay, so we multiply by -3. From 6 to -12. Okay, so multiply by -2. From -12 to 36. Okay, so -3 again from 36 to -72. -2 again. So there's a pattern there and it repeats and it's very clear and we could figure out the terms to infinity, but it's not the exact same thing each time. So it doesn't fit with this particular type. The formulas that we'll see in a moment don't apply to situations like this. So we have to just be careful and know that we're actually dealing with a geometric one, not one that it grows and it looks like it could be, but when we look more carefully, we realize it isn't. The last one. Okay. So we could write this as dividing by 3 or multiplying by 1/3, same thing. And we notice it's the same thing for each of them, multiplying by 1/3. So yes, it works. that is a geometric sequence. Broadly speaking, we'll have types where our R value is greater than 1, absolute value of R is greater than 1, or types like this where our absolute value of R is less than 1. If the value of R is actually negative, that becomes a slightly more complex scenario, which we will not really deal with because we won't need it for our application. So we'll have these two big categories, R greater than 1 or R less than 1. Okay, so let's go on to first example here. So let's say we have the sequence. First term is 3, common ratio is -2. Write out the first 5 terms. Okay, so our first term. First term is 3. Okay, so the common ratio, we're not applying that to the first term, we apply it after the first term. So there's common mistake. So 3, the next term, this one is -6, next term. Okay. All right, okay. So there is our pattern for this. So just multiplying by -2 each time. Right, so like we had for the arithmetic sequences, we also have a formula for these geometric sequences. Very intuitive, it's what we expect. We just start with A1 and then we multiply by R a whole bunch of times. How many times? n-1. So just do, we have A1, 2, A3, 4. We start with A1. If we want to get to A4, we should multiply by R once here. A1 times R gives us A2. A2 times R gives us A3. A3 times R gives us A4. How many R's? n-1. 4 minus 1. So 3 of them. So it's quite intuitive. It should feel fairly natural. Yeah, like that makes sense. Just remember in the exponent here, there's a -1. The rest of the terms and labels are the same as what we used in our previous. All right. So here's our formula. Let's practice using this. So here is a sequence. Figure out what the 14th term will be. It should be possible to simplify this without needing a calculator. We can get a nice fraction result. Look for the shortcuts. 19. Okay, let's take a look. So just to remind us all, our formula here, A n equals A1 r exponent n minus 1. So we have all the parts that we need here. So A14 is A1, which they told us is 64. And that multiplied by our ratio R, which is 1/2, and our exponent, 13. So 14th term, n minus 1, 14 minus 1, 13. One over 2? Just 64. Okay. All right. So yes, so 64 is 2 to the exponent 6. I'll just do the exponent rules here a little bit slowly in case some people forgot some of those parts. The exponent, we can bring that into both parts. So 1 to the exponent 13, which is just 1, and 2 to the exponent 13, like this. Combine this. 2 to the exponent 6 over 2 to the exponent 13. I see now where you got the 2 to the exponent 19, you added them. What is the exponent rule that we can use to simplify this? Okay, so we subtract. If we're dividing here, and same base, we can subtract the exponents. So 2 to the exponent 6 minus 13, that's negative, well, -7, let's write it. So 1 over 2 to the exponent 7. And that number, 2 to the exponent 7. 128. We already figured out 2 to the exponent 6 here. So just that times 2 again, 1 over 128. If you are not really familiar with the powers of 2, so 2, 4, 8, 16, 32, up to at least like 2 to the exponent 10, they're very common, very, very useful. It's there's some value to memorizing those, I would say. Okay, so there we have our answer. It's a nice fraction instead of 0.0 ... whatever. Okay, I have one more example. All right, one more example here. So find the 12th term of this sequence here. $1,144, we think. Okay, so our 12th term here, same formula, A12 equal to, there's our first term here, 3. And what is our ratio? 2. Okay, we're just multiplying by 2 each time, so 2. And our exponent here, 12 minus 1, 11. So yeah, just that. So 3 times this, 2 to the exponent 11. We might know we might remember 2 to the exponent 10 is 10,020, sorry, not 10,000, 1,024. So just multiply that by 2, so 3 times 20, 48, and then multiply that by 3. And yes, we get this, 6,144. Okay, so just that's a simple formula for general term and just some simple practice with this. Let's go on to the next part, which will be about the partial sum formula. So we'll look at these and sort of see what's happening with the partial sum, and then we'll see how we can kind of get the formula from that. So first, let's just write out what the terms are, and then we'll worry about adding them up. So for this one here on the left, what are the 3 terms? What's the first term? 1. Next term? And 4. Okay. And if we continue that to here, we're being asked to just take that plus. What would the 4th term be here? 8 and 15, 2. Okay, also just powers of 2 again. And if we continue that here, or 28 to 56. Okay, so if we are then thinking about adding these up, if we add these ones up here, what do we get? 7. If we add these ones up here, what do we get? 63. Look, it has to be an odd number. We have a 1 here and the rest are even. It must be an odd number. Okay. And what would the next one be? Don't do it manually. Look for the pattern. What's the shortcut? What's the shortcut you can see here?
— 63 multiplied by 3.
Too big. Okay, look at the pattern that we see so far here. This, and then the next one. There we go. It's whatever the next term is minus 1. That's the sum of the previous ones. Yeah. Okay. Now we see it. $512 is the next term here. Okay. So when we are adding these up like this, there are always some sort of shortcuts and kind of patterns we can notice. Okay, but more generally, we have a useful formula that will let us figure this out, which is 2 actually. So these, sorry, there's one little mistake there. Let me correct that right now. I made one change. Okay. When we looked at the partial sum formula for the arithmetic series, and we had add up all the numbers from 1 to 100, and we sort of looked at, okay, let's make a pair with the first one and the last one, and how many pairs. It's sort of intuitive and kind of satisfying to figure out that formula. For this formula, you know, there's a derivation, a process to show how we get this, but it's not very like exciting or kind of satisfying like that. It's just a bunch of algebra. It's in our textbook if you're curious, but I'm gonna skip that. So this is the formula that we can use. Two things here. First, we have two of these formulas. Are they the same or are they different? Are they mathematically the same or different? Okay, so not just absolute values. If we take this one here on the left and we want to go to this one on the right, what would we do? Multiply by just -1? If we multiply by -1, we're changing the result. Can we do this in a way where we don't change the result? Okay, so there. So if we multiply by -1 over -1, it's just 1. So we are not mathematically changing the result. But the effect of this is to just take the signs on, say, on the bottom, and you just are flipping them. The R becomes positive, the 1 becomes negative. And we can apply the -1 to inside the brackets and do the same thing. And then we get this and this result. So mathematically, they are the exact same. You can use either one, you'll get the same result. The reason that we have two of these is that this one, if your R value, your absolute value of R is less than 1, here everything will stay positive. It's just a little more convenient, a little nicer to work with. On the other side here, if your absolute value of R is greater than 1, okay, then everything will stay positive. If you didn't do, if you did either one of them, let's say, if the R value was greater than 1 and you did this one, you just get a negative on the top, but a negative on the bottom. They cancel each other out. It's not really a big deal, but it's a little more convenient to use them like this. So please note here, this is a common source of mistake. Here it's R to the exponent n, and then -1. Here the -1 is not in the exponent, it's just separate. The general term formula, the -1 is in the exponent. So important difference, make sure you remember those separately. All right, so let's put these to use and just add some stuff up. I hope you have these written. Let's find the sum of the first 20 terms of this thing. We don't want to add them up, but manually use the formula, find the result. All right, the exponent on this one is going to be kind of big. If you can simplify it as much as possible without evaluating the exponent, then that's fine. Just simplify as much as possible. Okay. So are we ready? What's your, what, without evaluating that last exponent, tell me. Okay, let's check. So S20, our formula here, our R value is greater than 1, or okay, so greater than 1. So we have, I'm gonna need a little more space. Okay. All right, we'll do it here. So our first term is 7. Inside our brackets, we'll have R, which is 2, to our exponent N, which is 20 minus 1. And on the bottom here, R not to the exponent, just R minus 1, which is 2 minus 1. So that's just 1 on the bottom, okay? So 7. Actually, you guys have this here. 2 to the exponent 20 minus 1. If I were to maybe expand this a little bit, 7 times 2 to the exponent 20 minus 7. I look at that and I know 2 to the exponent 20 is 1,048,000. But I don't remember the last little bit, 500 something maybe. Okay. So let's just say this is simplified enough. And if I were to give you a question like this on a test, I would not ask you to spend like 20 minutes figuring out this exact thing. Just this is enough, and simplify as much as possible. Okay. So, but if you want a little kind of shortcut or thing to help you remember these, two to the exponent 10, we said is 1,024. And 2 to the exponent 30. So it's basically 1 billion and some stuff. Dot, 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 comma, dot, 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 comma, dot, dot, dot. So 1,000, 1 million, 1 billion. We're just adding 3 zeros each time it goes up by 10 like this. So just a little pattern. I don't remember the exact number, but that's just general sense that helps you remember it. This is the first math course. There's honors math, which is mainly calculus. That's an optional class. Okay, but you will have a statistics class in your second year. There's a lot of math and statistics. Okay. Also microeconomics, macroeconomics, accounting, finance. The reason I am teaching you all of this stuff is because those professors want you to know this. They are going to take all of this and apply all of it. You'll see that when we get to our interest stuff, finance, accounting. These are very general purpose math skills. Okay. I explained all that in the very first class. A good business runs on numbers and data. You need math to understand that. Okay, so the last thing we'll look at is about these infinite sums. We had the partial sums, but what happens when our numbers get really, really big here? Okay, so let's use our formula. We won't write out every single term here. We don't need to. We'll just use our formulas and kind of see what would happen. So let's write out our sum for the first 10 terms and figure that out. What is our first term of this series? 6. So 2 times 3 to the exponent 1, 2 times 3, 6. Okay. And our R value, 3, common ratio, multiplying by 3 each time. So 3, and our exponent, 10 and minus 1. And on the bottom here, R minus 1. So 3 minus 1, that's just 2. All right, let's simplify a little bit here. 6 and 2, that just turns into 3 times 3 to the exponent 10 minus 1. And simplify a little bit more. Minus 3. Okay. So this A1 term, when we go to the next one, we're going to do this again for here, but we can just be a little clever about this instead of rewriting everything. The A1 term is not going to change. The R term is not going to change. The minus 1, that's not changing. That's all changing. So the only thing that's going to be different is this exponent. And here 10 gave us 10, and then we added 1 here basically. So it will turn into that 11. So we can directly write what the next one will be without doing all that extra work. So tell me what this would be. Some of the first. Okay, so 3 to the exponent 101 minus 3. Okay, so it's getting a lot bigger very quickly here. And what about our last one? What if we wanted to try to do this all the way up to infinity? Okay, so 3 to the exponent infinity minus 3, that's a little weird. 3 to the exponent infinity, what would that number be? All right, also infinity. And if we take infinity minus 3, also infinity, we still can't count it. So our result is just infinity there. So kind of big, really big, too big. So for a geometric series, if your R value is greater than 1, if we add them up to infinity, we should understand that the sum will be infinity. Eventually, even if it grows slowly, it will grow to infinity eventually. We should understand that. So I'll have this slide here, which will just explain this in a little more detail. So looking at our formula a bit more carefully, let's see how that happens, where that infinity comes from. So first, absolute value of R, if it's greater than 1, then when n approaches infinity, as n gets bigger and bigger and closer to infinity, what happens to the first term, the A1 value? Does it change? Nothing. It's just that stays as A1. Okay. What happens to the R value? Nothing. So it's just R, and so n is approaching infinity. Okay. That's the easy part. So R to the exponent n as n approaches infinity. Okay, so that will approach infinity. That minus 1, infinity, and also infinity. So thinking about our formula here, we can see how it makes sense that as our n gets really big, eventually our sum will go to infinity if the R value is greater than 1. The absolute value is greater than 1. That part's very important. All right, let's look at the opposite situation. So very similar, except now our R value is less than 1. So let's take this thing and let's simplify. So S10 here, what is our first term? 2/3. What is our R value? 1/3 and to the exponent n. So 10 minus 1 and divided by 1 over. Okay, so here's something. Remember our formula? We have the other. Okay, so let's use the other version of the formula that will just make our negative sign kind of a little easier to deal with. So 1 minus 1/3 the exponent 10. And then on the bottom, 1 minus 1/3. Okay, so let's simplify this. So 2/3 over 2/3. And on the inside here, 1 minus 1/3 the exponent 10. Okay, so these cancel out, these eliminate each other, and 1 minus 1/3 to the exponent 10. All right, so 3 to the exponent 10 is a pretty big number. So 1 over that is going to be a pretty small number. So 1 minus that whole thing will be pretty close to 1. So it'll be like 0.99 whatever. All right, let's write the next one. One minus 1/3 to the exponent 100. Okay. And this is going to be even closer to 1, a little bit less, but very close. And then let's imagine if we took that off to infinity here. 1 minus 1/3 to the exponent infinity. So look at the pattern that's happening here. This number was close to 1. This number is even closer to 1. Less, but very close to 1. But this will suddenly turn into infinity. That doesn't make sense. Okay, so what do you think this will get close to? Okay, very, very close to 1. So maybe equal to, where can I write a question mark? Maybe equal to 1. So let's look at our formula, the same thing we did for the other one, and see what will happen. So down here on the left, these are all the same as last time. So if our absolute value of R is less than 1, if n approaches infinity, A1 is still A1, R is still R, n is approaching infinity. But this part on the right is the key part to remember here. So R to the exponent infinity will approach what? If our absolute value of R is less than 1. So a fraction, let's say just 1/2 to some really huge exponent. What will that be close to? 0. So this, our R to the exponent n will get closer and closer to 0. So this is what you guys are trying to answer. 1 minus that thing will be what? Approaching what? That will get very close to 1. So now A1 times that thing will approach A1, first term. So it kind of looks like we could just forget about that part. All right. And that is the formula. So if our R value is less than 1, and we add up all the numbers to infinity, the answer is not positive infinity or negative infinity. It's just some number. It's like 5 or 22 or -6 or something. It's just some regular number. Here's another way of thinking about this. Let's say, so I'm standing here and there's the wall over there. And I say, I want to walk to that wall, but I'm going to do it by walking half of the distance to that wall. And then next, I will walk half of the remaining distance. And then half of that remaining distance, and then half of that. And I'll get closer and closer by reducing the distance by half each time. Would I touch the wall? Okay, why not? There will always be some tiny distance. We're taking some small number, reducing it by half, and it gets a bit smaller, but there's always something left. That is what a physics person would say. They're thinking in the real world, there will always be some distance. In the math world, we can go beyond that into this abstract. We can actually go to this point infinity. And at the point infinity, there's nothing left. And we've gone all the way. We can touch the wall. Because in the math world, we go to that abstract limit. That's exactly what's happening here. This is only possible if we imagine not getting close to infinity, but actually going all the way there. Okay, so this is where math gets a little bit abstract, but at this infinite sum here, this is all it is. This is all we need. Okay, so infinite sum, if the R value is less than 1, can just be a number. It's not infinity or negative infinity. Only true for these geometric series, or not true for the arithmetic ones. It can be for some other types too. This is called a convergent series because the result converges, gets closer to just one thing. If we had this on a graph, then the pattern would be like this, and then there would be some line, and it would just get closer and closer to that line. Well, at the point infinity, yes, it does. That, okay, that is a very good question. You can ask a philosophy professor that question. If we have the other type here, if our R value is greater than 1, this is what we call a divergent series because it doesn't approach anything. It just keeps going further and further away. So this would grow like this and would just shoot way up, and it doesn't ever approach any kind of one number. It just grows to positive infinity or negative infinity. Okay, so convergence and infinite sum. In this case, if these things are true, geometric and R is less than 1, then we get the special result. All right, so I have some examples with this, but we'll just kind of leave this idea to kind of soak into your brains over the next 2 nights, and then we'll come back and do some examples with this in the next class. But for now, I want to just do a quick preview of interest and how we will be applying these things, and just introduce some terms here. So interest, of course, in like the money finance version of interest. Maybe not all of you have a whole lot of experience with like loans or credit cards or whatever. So just for people who haven't had any experience with that, what is interest? Just explain it in the most simple term that you can. Okay, so a loan with some percentage added. Why do they add a percent? Yeah, why? That's who. Why? If you're paying interest, you owe the bank money. Okay, but why? Why do we have this? Why do we care about? Okay, that's why we do investments. That's not the concept of interest itself. So just very simple terms. If you rent a thing, if you rent a house, you rent an apartment, you rent a car, that means you get to hold or use that thing. You get to live in the house, you get to drive the car. But for the privilege of borrowing and using that thing, you pay money. You rent the house, you rent the car. Interest is renting money. So that's the most easy way to think about it. So I get this privilege of holding this amount of money and I can spend it on whatever, but whoever I'm borrowing it from, I need to pay them rent for that money. And the larger the amount of money, the more rent I pay. Just like if you rent a bigger house or a bigger car, you pay more money for it. So that's the idea. So it's the fee that you pay to rent money. Or when you rent it to other people, it's the fee that they pay you. We are going to need a few different terms to talk about this. I'll talk about the numbers next time, but for today, I'll just introduce the terms. So we will need this one. So lowercase I is our interest rate, which is always expressed as a percentage applied to whatever the base thing is. The base, the original number, we call the principal of the loan, principal. So we'll use this P symbol here. It's the original amount of money that went in. Capital I is the dollar value of the interest. So lowercase I is the percentage, the rates. Capital I is the actual dollar value based on that interest rate. Excuse me. T is our time, almost always expressed as years. And then the last thing we'll need, AT. I'm not sure why A, but lots of textbooks use this, maybe accumulated or something. But this is the value after T years. So the principal is your starting point, and then it grows to this final result. Your principal, and then plus some amount of interest gives you that value. And after 1 year, or after 5 years, or whatever. We'll see two basic types, simple interest and compound interest. We'll look at the formulas next time, and we'll see how those are very connected to these arithmetic and geometric sequences and series. Okay, so some terms, some labels here. We'll be using all of these in the next class. I think that was it. Okay. Does anyone have questions? All right. So next time, something up. All right. So we have a formula for general term, both for arithmetic and for geometric sequences. Two different formulas, need to remember. We have formulas for partial sum for both of these types. And we also have a formula for infinite sum, specifically for the geometric ones. And we've learned how to write everything as this summation notation with this big sigma thing as well. So we'll do more practice with that stuff, the infinite sums and sigma notation in the next class, and then get to interests. Review questions. 12.1 in our textbook has the summation notation stuff, and 12.3 has the geometric sequences material, and lots about interest next time. After this, we will talk about polynomial equations, like so just equations of things that look like this and this. And then we need to understand that before we go to the calculus. So we'll have maybe a week and a half to review some stuff about that, then calculus. Yes, I have attendance papers here you guys can sign. All right, we're finished. Thank you everyone for listening. See you on Thursday.